Hello, everybody. Everybody, sorry for my voice. I lost it somewhere yesterday on the road, but I hope I can make it. My first presentation today is about risk-based approach to structural integrity assessment of penstock critical components. Some of co-authors are also present here. And this will be a presentation of work, which is basically engineering work, not rocket science. You will see how we use some very basic engineering tools and some basic engineering tools to assess structure integrity of critical components which are in the critical state. So we are talking about penstock in a hydropower plant, which must not fail under any conditions. This is why I call it critical. In a situation when NDT or other examination detect some so-called unacceptable defects, there is a big problem. What to do with equipment like that? Any stoppage is too costly. Repair, that's an option, but it depends on how long it would take in terms of time. Replacement, that's something that we need to avoid if possible. To do so, we need a reliable and conservative assessment of structure integrity. And our job as engineers in this case is to provide a risk-based analysis so that management can decide what to do. Risk-based analysis here is, reduced to engineering assessment to some basic equations of fracture mechanics, or in case of slightly more complex geometries, to finite element method analysis and application of its results. A failure assessment diagram is our tool that we are using to get this risk assessment, which we present in a form of risk matrix. Wrong way. Risk matrix is not defined in a unique way, but here we use the most common way, which is 5 times 5 matrix, where the risk is treated as a consequence times probability. Both of them are here separated into 5 segments from 0 to 1, and in combination we have low risk at one end and very high or extreme risk at the other end. As for the consequence, we take care about health, safety, environment, business, security, and maybe even some other aspects. So this is a kind of estimation, not exact science. We cannot exactly measure it, but there are some recommendations. And as I told you, in this case, it is a high consequence. We will have it either as extreme or high, depending on a component. I already said some words about what we are dealing with in this presentation. So just to give more information, it is about hydropower plant Peručica in Montenegro, where there were some unacceptable defects in so-called inlet elbows. unit 6 and 7. I'll present soon one of them, that you see what we deal with. And also another component that was a problem in this respect was the branch. In the case of the elbow, a number of defects were detected. As the most critical one, sorry for this, as the most critical one, you can see this one, 500 millimeters long and 20 millimeters deep. So out of 42 up to 52 millimeters of thickness, this is about almost half of thickness which is occupied by a defect. This is a cast iron and very rude one in a sense, a big one, not a precise casting, just classical casting. So this is why thickness is varied so much. In any case, our idea to get a probability is original one, as introduced in a decade ago in one doctoral thesis. You can see here failure assessment diagram, and let's think about a point somewhere here, like that, as if we had already calculated our coordinates and position point here. Distance from that point to 0 is one quantity that we need, and the other is if we go the line, if we draw the line from 0 through this point up to the limit line, that's another measure that we use to make a ratio. So ratio between distance from the point to the 0 and distance from the limit line to the 0 is practically our probability. Reasoning behind is simple. If point is close to 0, this ratio is also close to 0. If point is close to limit line, this ratio is close to 1. So not exactly in mathematical terms probability, but we use the term and don't excuse it. So to get to a practical point of this talk, you can see what are the input data. This material is classical engineering material, cast steel with relatively low fracture toughness. We estimated here its value based on our previous experience and literature data. Loading is defined here as well as geometry. And in this case, it is a simple task. In this case, we just use basic fracture mechanics parameters to, and that is stress intensity factor, to evaluate K1. We did that in two cases. One is not so conservative when we took into account real dimensions of a crack. The other one is if we assume that crack goes all the way through the circumference, so that would be more conservative one. For those two cases, we also calculated the net stress and divided it with critical stress to get the x coordinate. You can see it here, it's the same, of course. And then for the K1 versus K1C, we obtained two values and 2 points, both of them in the safe region. After calculating, after this simple calculation and estimation of the consequences being high in this number 4, we could position our crack either in this field here or there. Of course, this edge crack, which is conservative, has somewhat higher risk, but both risks are actually estimated as high. So that was the first case. The second one is about the branch. Branch is more complex. Also, it had some unacceptable defects. You can see here the branch. You can see also here how this looks in reality. And here are some other details. It is about welded joints now. Point here is that we couldn't just calculate the circumferential stress and say this is our acting stress, remote stress that affects the crack, but we had to carefully both measure and calculate the stress. For the measurement, we used strain gauges, and for the finite element method, we used some sophisticated techniques to get as close as possible, because this is actually very tricky geometry. Maybe it doesn't look like, but one of the toughest tasks that we had in a finite element analysis. Based on these two measurements, we finally concluded that acting stress is, as you can see here, in the critical point about 115. And from that point on, we could use the same procedure to calculate coordinates and to position this critical point somewhere, once again, in the safe region. Therefore, this central crack, which is in this case, let's say only 7 millimeters, to remind you, elbow had it for 500 millimeters. So the risk is also lower. It is in the medium region. Thus, to come to conclusions, we did our engineering job. We provided management with the results, and they decided what to do. Based on this analysis, they decided to repair defects. And that was done successfully because, in the case of elbow, they repaired it. In the case of branch, they left it as it is. Because one of the reasons, not only because risk analysis indicated that way of thinking, but also elbow is much, much simpler to repair. Branch is not a simple task at all. So I think I already made the conclusions, and thank you for your attention.
Thank you, Professor Sedmak. We are open for any question. Yes.
Did you consider doing some crack growth analysis to determine how the risk would change over time if you'd continued running it without repair?
Let me think. Yes, yes, we did. In the case of elbow, there is about 100 startups per year, and for that number of cycles, we did some calculations which show that fatigue is not a big deal, but it's certainly a point for consideration. Actually, there was a bit of quarrel between people who detected these cracks and who wanted to not only to repair it, they wanted actually to replace the elbow. Well, we prevented them from doing that because that would be about a year and a half of stoppage. And in a way, together with management, we forced them to repair it and put it back in 2 months. And to prove our case, we also considered that. Thank you for the question.
Thank you. Any other question? No. Okay. I think that we can move to the next presentation.
Yes.
Held The presenter is also Professor Sedmak.
Tell me what is the time. I have no idea how much I used already.
You are?
Well,
This is for the previous presentation, okay? Left
oh,
5 minutes.
good,
So
good, good.
You are,
Excellent. That's much better than I
in
thought.
timetable. Okay. So the next presentation title is Impact Toughness of A516 grade 60 steel welded joints.
Thank you, Dario. Well, once again, something practical, although with a bit of maybe deeper science, at least from material point of view. So here we deal with impact toughness of certain more or less classical carbon steel used for welded structures. And here we focus on the welded joints because critical area in respect to impact toughness or any toughness, as you know, of course, is in welded joints, either heat affected zone or weld metal. We do have TC18, by the way, to deal with that. So this is what is also written here. We have used instrumented Sharpie toughness pendulum, which can separate crack initiation and crack propagation energy, which is very important issue. As it turned out in this case, not so important for what we aimed to do. It was almost irrelevant because we actually tested these welded joints starting from the room temperature down to 0, -20, -40, and -60. And the idea is to evaluate ductile to brittle transformation temperature. Actually, our main task was to find out how these welded joints behave at -60, because there was an idea to use this steel as a pressure vessel, as a tank for CO2, liquefied CO2, which is operating at approximately -60. As I told you, this steel is low alloyed, very low alloyed carbon steel used in pressure vessels, just as I mentioned, for storage. And it has, well, not exceptional, but good mechanical properties. Whenever I take data from literature, all mechanical properties are exceptional. I don't know if you notice that as well. So be more realistic. Good one. Actually, the best feature of this steel is that it is cheap, and still it can serve as a good material for many applications. In this case, plates were of thickness of 15 millimeters, and welding was done by manual arc process with some advanced electrodes alloyed with nickel. I'm not sure that I have tables 2 and 3 here. Let's see. No, I don't. It's in the paper. Sorry for that, but it's quite classical. Nothing interesting too much. You can see, well, barely you can see in this figure here how weld metal looks like. There were a couple of passes and X type of groove. Microstructure, typical for this type of steel, and then for heat affected zone and for fusion zone and for weld metal, pretty different type of microstructure, although you will see that behavior from point of view of impact toughness is maybe even unexpectedly similar. When I first saw these microstructures, I thought that it would be the difference would be much more expressed. So sharply instrumented pendulum, it's how to say, almost forgotten, but very practical tool to at least estimate, if not evaluate, material behavior, material crack resistance to cracking. Material crack resistance, sorry. So what we get from this instrumented pendulum is force versus time diagram, and then using it, we can separate energy to initiate crack, which is practically the area up to this point, and then energy for crack growth, which is remaining area. In this case, you can see that energy for crack initiation is much larger than energy for crack propagation. Knowing data like this, you can conclude about crack behavior of material, because if crack initiation energy is much higher than crack propagation, that is one way of crack resistance behavior, and completely different is the other option. If we have material with low crack initiation energy, then we have to be much more careful with its initial state. To be extreme, I can say such material must not contain cracks. So, in any case, we did testing, as I just explained, and obtained typical curves, obtained curves for force versus time for heat-affected zone, for well metals, for base metal, and then some of them, as typically obtained, are shown here at -60. Focus was here on -60, and on getting temperature dependence of total energy versus temperature. So here we have, as our final result, base metal, heat-affected zone, and well metal. You can see at once that it's quite similar. In my experience, which is a big one, differences are usually bigger than this. So this steel behaves nicely in a sense of its welded joints. Using diagrams like this, if we put 27 joules as a limit, we can get ductile to brittle temperature transition. It would be somewhere here for base metal, somewhere here for heat-affected zone, and somewhere here for the weld metal. More concretely, base metal had it at -70, heat-affected zone at -65, and weld metal approximately at -62. Since our idea was that we use this steel at -60, we can say that it has passed the examination. We can use it, although it is quite close to being not usable. But to emphasize once again, these differences are really not big. So having weld metal, which is with high enough impact toughness at -60, that's good news. That's really recommendable for this steel. Now, just to explain why I didn't mention anymore crack initiation versus crack propagation energy. Here this was the wrong move, okay. Here, it's total energy. Because, first of all, we need total energy to estimate this transition temperature, but in this case, crack initiation energy was very low for all areas, for all zones, So total energy is practically the same as crack propagation energy at -60. And this is why we didn't care too much about separation of energies in this case. So that's all for me in respect to presentations.